Okay, it is my pleasure that I can here and work with you guys and then present you this tutorial. And so, I'm going to talk about Sensor Web Enablement. So let's start from background, why we are talking about Sensor Web and what is a Sensor Web. So background. So there's a law called Bell's Law for the birth and death of the computer classes. So basically Gordon Bell is a researcher in Microsoft Research, and he reviewed, about history of a computer. And he said about every 10 years there's a new computing class. And then so he predicted that the coming rapidly are billions of cell phones for personal computing and tens of billions of wireless sensor nets to unwire and interconnect everything. So in 1951, a man could walk inside a computer, and by 2010, well, computers are beginning to walk inside of us. So right now we start to see a lot of sensors just surrounding us. And then, for example, my house, I have a Wi-Fi thermostat. I get to control my house temperature. And then phone, your Samsung phone. We have lots of sensors in it, and we have a lot of sensors surrounding us and around us. And actually, each sensor, a lot of sensors, they have computing power, so they are small computers. And then also the other number is a number of internet connected devices. That means a sensor with computing power and with internet connection. They will reach between 50 to 60 billion by the end of the decade. So that's the other number. And you can see a lot of those numbers, 50, 60 billion, 20 billion, or 30 billion. So basically it's a lot of them. And so somebody told me that in every conference we have to talk about big data. We want to be trendy. So I'm going to talk about big data. So how many of you are using social networks? Yeah. Is Facebook popular here? Yeah? Okay. Because sometimes each country has their own, right? Yeah. Okay, so for social networks, there are a lot of data set, right? So basically, I think while I'm talking here, a lot of people are using Facebook and plus, click like, there's no dislike, but click likes. So a lot of things are happening on social networks. And for example, in 60 seconds, there will be how many queries? For example, it's like over 700,000 queries in 60 seconds. And then on Facebook, anything from Facebook, a lot of pictures, a lot of videos. For example, on YouTube, every 60 seconds they have 600 plus new videos. So a lot of data. And the other guy actually predicted that within the next 3 to 5 years, the growth of the sensor data will be 10 or 20 times that of social media. So actually, sensor will generate more data than social networks right now. So when we talk about big data, there are 3 V's of big data. It's widely referenced in articles and conferences. So the 3 V's are, the first one is volume. So volume means a lot of them. So 5.6 billion mobile phone, for example, a lot of mobile phone. And then 50 to 60 billion internet connected sensors by 2020, and a lot of sensors. So the first one is volume. Second one is velocity. Velocity means the speed they are generating data. They are spitting out data. So for example, on Facebook, every month they have 30 billion pieces of content shared on Facebook. Okay. And then if we apply to sensors, if we have 10 to 50 to 60 billion of sensors, and then it will be a lot of data. And because sensors, they generate data streams, right? Continuous streams. And finally, it's the variety. And then variety means the data sources, traditionally in the database, they are homogeneous. But right now, we start to see like the variety of data sources. So many kinds, fragmented, no sampling scheme, no metadata, no quality control. And then, in my opinion, variety is very difficult, and this is our focus because we are doing standards, and then we're trying to tackle this variety problem. And SWE and OGC's focus is for variety. But basically, these 3 V's all together make the problem very, very challenging. So I found this. I hope hopefully this graph will make sense to you. So I look at this. I found Sensor Web. We have a long tail. So if you look at the, so we put every sensor in the world here, okay, like a histogram. And then the first one is the most popular one. Popular means, shouldn't say popular. The one generate most data, okay, or the most, the easiest to access, okay. And then that's the first one. And then these one are the small sensors, means they don't generate a lot of data, or they are very difficult to find. So we rank them, put it all there, and then we find there are sensors already available. They don't even need suite, okay? For example, the weather office, the space agencies, they put their data online, okay? And then they are easily accessible. They generate a lot of data sets, okay? And if we only have a few organizations, actually the interoperability problem won't be that big, right? We still need interoperability. And next one, we have the medium ones. So more organizations that collect data. They don't collect a lot of them. Okay, they are medium size and then sensor arrays. And normally they are operated or published by a province, the state networks, or some big research networks. And then we have this kind of data. Okay, but there are a lot of sensors here, way more than these, the combination of these, okay? And these sensors, they all generate some data, and they are not easily accessible. So right now we are currently missing sensors, okay? We have a lot of scientists here, I believe. And then, of course, you collect data, right? But is your data accessible somewhere? I guess not, okay? And then I know a lot of scientists, they collect data, 30 years of data, okay, and then they put data, and it's my precious, they don't share with others, and put them in their drawers. So they are missing data. So actually, but one reason they are missing is because the technical barrier to publish those data is very, very high. So therefore, they have no means to publish their data. So if we have standards, and then we have the tools to lower the barrier of publishing, finding, and using sensor data. And for example, in the past, how do you publish web page? You write your own HTML, right? And then so you have to know some computer stuff, right? You have to write your own HTML in order to publish something on the web. But right now, how do you publish something on the web? You simply log on Facebook and click like. You publish something. Or you write a blog. Or there are millions of ways to do that. It's very easy. You don't even need to know what's HTML. But this standard behind the scene, but there are tools allow you to do that easily. So if we can lower the bar, and we are able to capture these kind of missing sensors. And we know we have a lot of them. Okay, the number of missing sensors is much larger than the number of currently available sensors. And SWE is a critical component, so we can tackle the interoperability problems. And the other is we need the good tools. So we lower the barriers, and then we can capture these kind of missing sensors. Okay, this is one example. A colleague of mine, and he did a project for near North Pole, and then basically it's the local people there, local people there. They go there and write their Ski-Doo and then collect data. And very nice data sets, and know where are the, basically to find where are the wild animals. And where are they right now? Missing. Okay? There are tons of these kind of projects and data that are not accessible. Okay. So this is background information. We have a lot of sensors, and somehow we want to capture all of them and form a sensor web. So sensor web value. So I would like to use this one to illustrate the value. Let's say how to link different sensor networks. Let's say I have a hypothesis. If I can control the traffic network, and I can control the air quality of the city. Does it make sense? Kind of, right? I think this hypothesis makes sense. But how can we validate it? Do a research about it? You need to access two different sensor networks, right? But right now, how do you do it? In many cities, you still need to call the person in the traffic network and call the other person for air quality and back them. And after a year, you get data. Okay. And then think about it. A lot of research hypotheses, okay, need to use the kind of sensor networks and to do their research. So that's the need for sensors. And two main formats, and everybody speaks their lockdown languages, and then there's typical interoperability problems. So we have three different levels: technical, semantic, and institutional. And SWE mainly address technical interoperability, but also address some semantic interoperability, like the phenomena. How to define phenomena? You need some semantics, or taxonomy over there, or dictionary over there. So that's the two. Okay, institutional is the most difficult, but that's not something we can address. But SWE mainly on these two levels. So I want to connect sensor network to sensor web. So that's the vision. Let's say. So this is the vision. We have a virtual globe system like this, and we fly somewhere, and then you see this, and then we throw a query into it. Okay, show me the sensors I want to use. Okay, like weather station or anything about water, and then bam, bam, bam. It shows the sensor and allow you to query. You even don't need to know what's. So you can query the physical world from anywhere at any time without knowing the implementation details. So that's the vision. So to be a little bit more realistic, so we want to have the vision is want to have a sensor web browser, and then somehow with a registry or a search engine, a way we can do resource discovery to find where are the sensors available we can use or we can connect to, and then we query it using some filtering, and then the search engine or the registry tells you, okay, you have this three fulfill your query criteria, so air, water, and smartphones. And they are in three different servers, so you are able to connect to them and put them together in a same coherent environment. And this is our vision. So think about it. If you do your science project, you don't need to worry about data. You go to a browser, you query, and bam, 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 tells you the data. And you can connect them in a same environment. By doing that, we can focus our time, efforts on how to use the data rather than where to find the data. And then I love this, innovation in assembly. So we can innovate by putting things together. And for example, a great thing about human history is food. And innovation about food is how to put different food together and make a new dish, right? And here is, we want to have a web of sensors, so putting different sensors together to make an innovative applications. And SWE is the enabler for that. So, how to do that? An open standard-based approach. For example, www, World Wide Web, basically they are standards, okay? And then you can have different browsers, Opera, Firefox, okay, Chrome, IE, okay? You have your, I'm sure you have your favorite browser, and you can choose one and access the websites. And Sensor Web should be similar like that. So Sensor Web is, if you look at the whole system, from the sensor all the way to the web, and then there's a lot of standard stacks. And then OGC, we are sitting at the very, very top, so application level. I think today other speakers will talk about that. So, Sensor Web Enablement. So Sensor Web Enablement SWE is a web service model or a service-oriented architecture. So basically, there are interactions. So for example, we have three roles there. The first one is we have services. For example, we have services. So each service, for example, is a sensor observation service. They publish their sensor through interface online. And then we have a registry. So somewhere they can publish or make them available to let others know, okay, where to find them. So the first one is publish. So when it's sensor online, you publish to the registry. And then, so the client can search the registry or search engine and to find what's available. So distributed computing 101. The first step is resource discovery. So find where are the available resources we can use. So a client find through the registry. And finally, the client is able to connect to a service there. So what's required in order to fulfill this kind of architecture? So first one is, in order to talk to or bind to these kind of services, we need the standard service interfaces. So we know how to interact with these services, okay? A standard way how we interact. And then the second one is the languages between them. So standard information models. So you send a request, so you know what request to send, and then you also need to know what information models. Okay, and so that's the language between them. Okay, they need to speak the same language. They can understand each other, and then these are the two major components in this kind of SOA architecture. It applies to ODC Web Services, OWS, WMS, WFS, and also to suite services. So these are the first one is the standard information model and schema. So that's the suite. And the second one is the standard web service interfaces. In suite, we have observation and measurement, O&M. So basically, it's the core model and schema for observations. And the second one is sensor model language for institute and remote sensors. It's a core models and schema of observation processes. Support for sensor components, geo-registration, response models, post-measurement processing. So first one is for observations, and we'll talk about what do we mean by observation later. And the second one talks about sensor, and we'll talk about what does it mean by a sensor later, because we need to formally define those. And after that, we know what the models and schema we want to use. And then finally, the second one is we have the standard interface, so we know how to interact with the interfaces, the services. And the first one is sensor observation service. So basically, each service has a certain function. For example, observation service provides observation. That's the main function it does. Sensor alert services. So as you can see, I graded a little bit because this is right now it's a new service standard and coming up to replace this. It's called sensor event service. So, but this one provides alert. So each one provides a function or major function. And third one is sensor planning. So this one provides tasking and planning. And web notification provides you notification. And finally, registry provides you how to define basically resource discovery. So each one provides a certain function, okay? And they use this kind of these models. So let's dive into the information models. And we'll mainly focus on observation. So when we talk about models, we have conceptual, logical, and physical. And then in GIS, we have feature, in OGC, we have feature and coverage. And this morning, we talk about features and coverage as well. And then, or in GIS textbook, this is called object view, and this one is field. It's similar. And right now, we introduce a new one called observation. So that's a conceptual and logical model. And then in OG standards, there is a, I think it's a top 20 is observation, abstract specification there. And then that's defined, describe what's the conceptual logical model of in observation. But also the other document talk about how to implement the model with XML and the XML implementation for observation. So we need to separate the idea, the concept of information model and encoding. Encoding is the physical model, how you implement the conceptual and logical model. For example, for coverage, we can use a TIFF to implement the physical model, or a feature, we can use XML or GML to implement, but we can also use JSON, for example, and so on and so forth. And so right now, diving, what does it mean by observation model? So before we can define standards, okay, we need to figure out, okay, what are major entities in the sensor web? So what are the entities we want to address here? So first one, we find there are three entities in sensor web: observation, phenomenon, and sensor, and their relationships. So basically, observation uses sensor. It's a procedure and to observe a phenomenon. And then the purpose for an observation is to describe a phenomenon. For example, we have an observation about a temperature, which is a phenomenon. Okay, and observation is, and the result of the observation could be 15 degrees Celsius. And then when you do that observation or perform that observation, you use a sensor. For example, a thermometer. Okay, and then the purpose of the thermometer is to observe a phenomenon. And then finally, you can define the properties of these three entities. And first one, in fact, actually, when we talk about sensor web, and most users' application, we are interested in observation, but not the sensors. So think about it. You are, for example, you are interested in temperature, but actually you are not interested in temperature sensor. You are interested in the temperature observations rather than sensors. So actually, sensor web actually is observation web in a way. We are interested in observations rather than sensors. Sensors are very critical information if you want to use the observation data correctly. And actually, in GIS textbook, there's a very standard table there, and talk about object view and field view. Okay. So if you look at it, there are this table like this, and we have X and Y, which is the location, and the properties. Okay. And feature model basically is we have the object with the location attribute, and these are the values for the attribute, the properties. Okay. So that's a feature view. For example, I have a car and a building with the location, and the building has attribute. Okay. So that's one view to look at the spatial geospatial objects. And the other way to look at it is the coverage view. So coverage view is focusing on the space. So you're focusing on the same property, okay, and their distribution in the space. For example, you have this value, and then you have so same phenomenon or the same property, and you have in this location, and you have a value in that location. You have a value. A typical way to implement a physical model is a raster. A logical model is a raster file. You, for example, you can use a TIFF, and each pixel has a value, and each pixel has a location as well. So look at this. Actually, that's the coverage view. An observation view, which is focusing on the observation itself. This one. So this is the observation itself. So observation and measurement will focus on this itself and the property of this observation. And then, so this is the observation model. And therefore, we define an observation as an observation is an event whose result is an estimate of the value of some property of the feature of interest obtained using a specific procedure. Oof, that's a long one. Okay. But actually, I told my students, you can use this one to make sentences. Okay, try to put some real-world examples there. For example, in temperature observation, it's an event what happened in space and time. Event means something happened, space and time occurrence. Okay, so temperature observation, the result is estimation of the value. Okay, so for example, a temperature observation has a value, for example, 50 degrees, and that's its estimation. Because if you use a sensor to measure it, you have some uncertainty. Okay, so estimation of the value, 15 degrees, of some property of the feature of interest. For example, if I measure this room, the temperature of this room, and then that means the feature of interest of that observation is this room. Okay? And then the property, which is the temperature, and the value could be 15 degrees. And that's the estimation. Okay? The result of value is 15 degrees. And it's an event happening in space and time. So that's the observation view. And so basically these are the properties of the observation, the phenomenon, which is an event, inherent event, and use a procedure. In this case, okay, Steve, you mentioned about sensor, but not procedure. But actually in here, we define procedure. Actually, it's a sensor. Why don't we just call it sensor? Because a procedure, a observation could be performed by a human, for example, can be performed by a process, a chain of processes, okay, derive the final observation. So as a result, procedure is a more accurate term, and more accurate term than sensor, because sensor makes you think about a sensor itself, right? And then each observation has a feature of interest. Okay, so think about it. When you put a sensor, you have something want to measure, right? And you want to measure the property of something, and that something is a feature of interest. A room, a room, a house, a road. Those are the feature of interest. And the other thing is, to have this kind of feature of interest really reconcile the remote and in-situ observations. So think about it. I have a temperature sensor, okay? So in most cases, temperature sensor thermometers, they are in-situ sensors. In-situ sensor means the sensor itself, the location of sensor itself, and then the feature of interest, they are inseparable. So close, so they are together, okay? So that's the in-situ sensor. Remote sensor means the sensor itself and then the measured phenomenon, they are not close enough, right? They are different. For example, a satellite, a camera, I have a camera, I take a picture, and you guys are my feature of interest, but the sensor is here. Okay? So location of the feature of interest and then the sensor are different. But if the temperature sensor is the same, unless you use a thermal camera. And thermal camera is that camera, right? So the remote sensor. So by using feature of interest, we can really use the same model, okay, and to describe this remote sensing observation or in-situ observation. Any questions? Very quiet. Okay, dive into further details. So this is the observation model, ONM 2.0. So look at the observation, okay, and we have the following properties. The first one is a parameter. So parameter is something here, an event-specific parameter. For example, instrument setting. When you perform an observation, sometimes you need to do some settings, right? And input to the sensor, and that's a place to put that. Or I have the other example later, so I'll show you that later. That's a name value, optional, 0 to many. Second one is phenomenon time. Okay, phenomenon time is the time of the result. Time of the result applied to the property of FOI. So for example, if I perform an observation right now, like temperature, okay, that's the phenomenon time, because that's the result applied to the property of FOI. There's a result time, okay, phenomenon time, result time. So what is result time? The time when the result becomes available. In some cases, for example, temperature sensor, I perform observation. The phenomenon time is this. And the result time, because I collect result right away, so it's almost the same. Okay, you can treat it as the same. So phenomenon time, result time is the same. But if I collect a rock sample, I bring it, so I collect a rock sample, and phenomenon time is the time when I collect a sample. Okay? But I bring it back to the lab, I perform an observation, and then the result time is different. Because the result comes later, right? Yeah, you need to send to lab and then do some processing, so the result comes later. Okay, and there's the other time called valid time. So valid time is the time period during which the result intended to be. Normally, it's used for prediction. Sometimes you have some procedures, you can generate some observation, but that observation is for the future, right? Weather prediction. So tomorrow's temperature will be 15 degrees. So it will be valid tomorrow, but not now. So actually, it will be only, and not the day after tomorrow, because after tomorrow, that prediction will not be valid. So we have three different times: phenomenon time, result time, and valid time. And finally, we have the quality, the result quality, to describe the quality of the result, and that's a type of the data quality element. So these are the major properties of an observation, and it's really can capture a lot of different use cases, including in-situ sensor, remote sensor, rock samples, and temperature, everything, which is great. Okay, so this is an example about the parameter. Okay, so we have a feature of interest here. This is a well, for example, borehole is a well, and then perform 3 observations. And the first observation is performed on 2009, August 1st. Okay? And then at that time, the parameters is that the observation was performed at the depth of 3.5 meter. And the next day, we also perform an observation, so measure something for this well. But this time, the depth is different. But this is for information only, the information item, for your information, okay? This is not the core of this setting, so therefore we can use a parameter to put that. And the third day, depth is different, 7.1 meter. So we can use a parameter to describe these kind of properties. This is one example. Okay. So this is a full, complete observation model. So basically it is observation model, and these I just described them. Result time, data time, result quality. And then you have a result. And the value of the result is very important because that's a value for the observation. Okay. And then you have a phenomenon, so that which is observed property. For example, temperature is observed property, water flow, and soil moisture is observed property. And also feature of interest, and then procedure, which is, for example, a sensor, the procedure you use to perform the observation. And you have metadata, basically the description about the observation itself. Okay? So this is an observation model. So let's look at some implementation. Okay. Let's look at this first. Okay, so let's illustrate, it's a real world example about an observation. So this is observation, okay? And then 23 meter per second is a result. And in this case, the observed property is the wind speed. And the value of the observation, the result of the observation is 23. And it has a unit of measure, UOM is unit of measure, meter per second. And then it was performed, the observation was performed at this time, 2010, September 16, 1 o'clock, 45 minutes. Okay. And it used a procedure here, and with the ID Davis 123 is this guy to perform this observation. And then the feature of interest is a house. Okay? So that's a house. So therefore, we can say the observation describe the wind speed of this house, or on the house, the roof of the house. Okay? And this is the result, estimation of the result, and with the unit measure, and this is the time. So for the whole thing is an observation. This is an example of a observation measurement in XML. So we have this open observation here. So we have description, general description, observation, test instance. This one is a fruit mass. How heavy is the fruit? Okay. And then name observation test 1. So we have phenomenon time in this block. And this one is 2005, January 11. And then the result time. And in this case, because phenomenon time and result time is the same, so you can have the link and reference to OT1T, OT1T. So these are the same. You can use this, so you know it's the same, and you can save some space. And this observation uses a procedure here. And in this case, it has links. Normally you have a link or a UID and connect to a sensor ML in this case. In this case, we can guess, without even looking into the detail, we know it's a scale, number 34. And we have these parameters. Okay? And this parameter is, name is a temperature. Why do we need the temperature? To know temperature when we measure a mass. Because the temperature changes, it changes, right? And then, so in this case, the temperature is Celsius. So we know the temperature of the time when we perform the observation. And then observed property here, and it has a link to a suite ontology. And suite is a ontology for geosciences. And then here is a definition there is owl, and then the mass. Okay, that's it. You can. So if you follow this link, you should be able to find the definition of that observed property. And finally, you have a feature of interest. Okay, and in this case, it goes to a WFS, get feature, and then so you get the information about that feature. Okay, it's feature of interest. Finally, is the result. Result is a 0.28 kilogram, and then that's the unit of measure, and this is the result. And whole thing is a observation XML instance. Okay. Any questions for observations? Okay, so after observations, we have sensors, the second entity, sensor. So we don't go detail in this case, and just to show you what are the components for sensor ML. And actually, each one of them is optional, so you don't have to have all of them. And in many cases, in sensor web, or, well, that's my opinion, we use sensor ML as a metadata standard, okay, to describe the sensor. But actually, sensor ML is very powerful. You can use it as a process chain. And you can ask Mike Bots how to do that. Okay, so the first part is the metadata of the sensor system. You have the identification, classification, characteristics, capabilities, contact, who owns the sensor, what's the capability of the sensor, what's the characteristics, and the classification, what's used for, identification, what's the name, the model number, so on and so forth. And that's the first part. And then a sensor has a position as well. So the second part, we can define position of the sensor. And sometimes get complicated because sensor might move. Okay, so you can describe the sensor position here. And then can describe here is the interfaces. So interface definition to access input and output. To allow the sensor to have interface and how it will collect the inputs and generate the outputs. And then this defined interface is there. And finally, after that interfaces, you list what are the inputs the sensor take and the outputs the sensor throw away or generate, and you can describe that. Okay, the good thing about describe input and output is you can put sensor together. For example, if the sensor or procedure 1, the output is the other procedure's input, you can make a process chain, right? And this becomes very important and very powerful. And finally, the components, collection of physical and non-physical sub-processes. So these parts basically allow you to do a process chain, and it does input, output, interfaces. And the first part is the metadata. Okay, and in many cases, actually, we only use the metadata. Okay, so these are two major information models for sensor web. First one, observation and measurement, and second one is the sensor ML. Any questions? So after we have information models and we can define the interfaces, basically is how you interact with the services. And in SWE, we have the following services. So each one of them is doing certain function. So the first one is a sensor observation service. So we define how you get an observation. Okay, that's the most important part. Normally we use that. And then how to get other properties of the observation. For example, I get observation 15 degrees Celsius, and I want to know the feature of interest of that observation. I can perform a get feature of interest, so I can get a feature, okay, of feature of interest data from using this call, or I can get the result. Get a result basically is a way to fetch a lot of observation in the same call, but without the metadata about observation. So only the result, okay, and not the whole bunch of XML. And describe sensors basically is I want to know what sensor performed that observation, and then I can use describe sensor. And in SOS, we have the profile, and there are mandatory observation operations and optional operations, okay? And get observation and describe sensors, they are the mandatory. And plus get capabilities, because get capabilities is the mandatory for all the OWS. Okay, and if you get feature of interest, get result, they are optional. So that means not all SOS, they have these functions. And then actually we have more function than that. We have other profile. You can also insert observation into SOS. Okay, you can register, you can change the capabilities, and there are more operations, but they are optional. The core is describe sensor and get observation. Okay, and then you issue the calls and to respond to the XML documents in observation and measurement. So that's SOS, how to get data. Okay, so actually how to get data. And there's the other one is sensor event services. Basically, you can subscribe to events. So think about it. Without event subscription, how can we detect events? You need to fetch data from SOS all the time, right? Like every second, get the data. And then when there's a spike, okay, I know there's something happened, right? And this is not very efficient because you are pulling data all the time, and bandwidth costs money. And Sensor Event Service allow you to register an event. Okay, so only send me notification when this event happens. For example, if there's a moving object, it's near you, and there's a notification to you. Okay, or the temperature of your house goes up to 20 degrees, send you a notification. Or when the window of your house was open, it's open, and send you a notification. So those are events. Okay. And is sensor planning service. So first one is observation to get the data. Some of the sensors you can task them. You can ask the sensor to do something, and you can use sensor planning service. So basically, it is you try to find is it feasible to get to task the sensor in this time and space, and then to confirm the tasking. Okay. So for example, you can actually I still remember back in 2005, and when we talk about sensor planning service, Ingo talk about an analogy is sensor planning service is like a flight booking system. So when you book a flight, what do? You go to the website, okay, and then you tell the website, say, I want to fly from Calgary to Seoul, for example, on this date and this time, okay. And then, so the flight booking system tells you, okay, we have the following flights available. Or the flight booking system tells you, we don't have any flight, please change the date. And then you said, okay, I change the date, I confirm this flight, and then the flight booking system, okay, the order is confirmed, here's your confirmation number, okay. So actually this applies to sensor planning service as well. You have a sensor, you ask the sensor planning service, okay, I want the sensor to perform an observation, for example, fly to Seoul to take a picture, and are you available, or is it feasible? And the sensor planning service tells you, okay, it is feasible, or it's not. And if it's feasible, you confirm. When you confirm, and SPS sends you an ID, okay? Just like when you book a ticket, you get the confirmation number. And then with the ID, you can check the status of the sensor. It's still feasible, okay? So on and so forth. Same thing like when you book a ticket, right? You have the confirmation number, you can check the flight status. So that's the same analogy over there. But today, we are not going to talk too much about SPS. And one reason is, I couldn't find any SPS, public SPS online I can test. But I guess not many people open their sensor tasking to you, right? Okay. Sensor registries, basically it's catalog services, allow you to find sensors. And this is very important because how do you know where are the sensors? Okay. And all these can hide the low-level protocols, IEEE 1451, POC, so on and so forth. Okay, so this is the architecture diagram. So by composing these services, we can do some a lot of things. So SOS basically allow you to access this font size is too small. And then SPS allow you to access the tasking, command and task sensor. SES allow you to subscribe the events, and catalog allow you to find where are the services, and so the client able to connect them. Okay. So this is one example about how you deploy it in a real world example. So let's say in this case you have two sensors, and then they upload their observation to a database of the SOS, and therefore the users they can request the data through the SOS. And then also, it sends the data to the SES as well. Therefore, the user can subscribe to the event. So when the subscription filter, okay, the subscription criteria has been met, and then you trigger the alarm and send a notification to the user. So in this case, you can really save a lot of bandwidth, or you don't need to pull data all the time. It's more scalable. But how do we implement this kind of a system, which is a very interesting research question, in my opinion. And then also for some sensors, for example, like remote cameras, monitoring cameras, and you can test them, okay? So this is one example. Okay, details about SOS. So this is how, okay, I think I talked about this. So in order to get the observation, you can use get observation. In order to get the feature of interest, you use the get feature of interest. And get the sensor metadata, you use the describe sensor. You get the results only, okay, and then you get the results. And these are the APIs you can use. But we have the next slide is more easier to understand. Okay, so right now you have a client, you have SOS. So how they interact? How can I get data from SOS? So the first one is the user need to send a request, get capabilities. I will show you get capabilities later. The main hands-on, okay? So send a get capabilities, and the SOS return you the capability document. So basically, tell the user what is my capability. So how many sensors I have, what phenomenon I'm measuring, and what are the time and space and the location of those services, okay? And then so the user know how to compose the next request. So by looking at the capabilities, user can compose the get observation request. For example, okay, from the capabilities file, I know you have temperature sensor 101, and then give me the observation of the temperature sensor 101, and during certain time, and then it send you back at 1 AM and fulfill your request. And then after you get the observations, you might be thinking, okay, I want to know more about what sensor you use to perform observation. And you can send something called describe sensor. So please give me the information about that sensor, and then the system returns you a sensor mail. So here's the information about sensor, okay? And sometimes you want to know more details about the feature of interest. For example, you know get observation about a 15 degrees Celsius, and you know it's a house. And sometimes you want to know details about that house, and then you can use the get feature of interest request and give you back a GML feature. So basically, these are the core operations in SOS, the interaction between them. I'll go over this. So this is a model for capabilities document, okay? And then the light blue ones, they are defined in OWS comments. That means most of or all OGC web services, they have the similar metadata. For example, the title, abstract, if the service is down, who should you contact, provider name, so on and so forth, and operation metadata. And then the dark blue ones, these are the SOS specific. So for example, in the insertion capabilities, that's for the SOS support in insert, you have these. And then this is more important, the content, okay? So every OWS service, they have content, but their contents are different. In the case of SOS, the contents are observation offering. So each offering basically is like a layer, and then, so different observation offering. And this is very important for you to compose a request. And the green one is the filter capabilities. That means tells you the service support what kind of filter. Does the service support spatial operands? Or does the service support temporal operands? And so on and so forth. So when you look at capabilities document, that's the structure of the capability document. So when we dive into the important part, observation offering, okay, and then it has the following components. So basically here, this part tells you what are the parameters you can use to issue the queries, right? And then actually you can find exactly same information in the metadata here. Okay? Here you can find the same information of this one. So in many cases you have a reference, go there. Okay? And then these are unique in observation offering. So when we talk about observation, we have the following properties, right? And actually you find these are matching the properties. You have procedure, observed area, phenomenon time, result time, so on and so forth. Okay? And this one allow you to compose the query. So let's do one. I hope my network is working. Okay. So this is a test client, and then it's sending send a request to one. I make it bigger. One of our SOS. Okay. And then we have some canned request in this case. So this is the example get capabilities document. So get the capabilities, we keep it bigger. Okay. And the service type is SOS. So basically it's to tell the SOS, let me know, please tell me your capabilities. So what do we have? And we can send. Oh, here it comes back. Okay. So here this is the capabilities I received from the SOS. And the first part, these are the, let's go back here. So the first part we have this. So service identification, service provider, operations metadata. So go here, service identification. So this one is a OGC SOS version 1.0. And then the title is Echo demonstration. Echo is a sensor we use in this case. It's a real sensor. And service provider is your sense on the website, so you know who should you call. And then if the service is down, there's a address, so on and so forth. Okay. Okay. And then here's the operation metadata. It tells you that what operation this service supports. In this case, that means this service support get capabilities. Well, it has to support it. And then it supports get observation as well. It supports describe sensor in this case. And these are the protocol support post. And that's it. So basically this service only supports 3 operations here. And content. That's very important in order to compose the query. So the content, first one is observation offering list. So we have a list of the observation offerings for this sensor. So the first observation offering is a echo node. So that's our sensor name. And the geo name echo. And there's a spatial reference system, EPSG 4326. And the location of the sensor or the feature or actually the observation area. So it's bounded by a GML envelope. And then the time available. So we know actually the data, this service has data since 2011 July and to actually it's like today. Yeah, this is near real time. I think we collect the data every 15 minutes. Okay, for more than a year of data over there. Okay, and here's are the procedures for this offering. Okay, this offering is Echo node, and these are procedures. And we can look at that, and then we know there's this solar volts, battery temperature, soil temperature, for example. And these are the procedure. Sorry. These are only one procedure. Procedure is this guy. Echo node is a procedure, and these are observed property. Okay, and this sensor perform the following observed property. Measure the following observed property: solar, battery, external volts, internal temperature, and soil moisture, for example. And then the feature of interest of this observation offering is this. So there's a link. You can get a feature of interest. And here's the response format. So what are formats supported by this SOS and the result model? You can ask for measurement model or observation model. Measurement means this numerical model. The results are numerical. Okay, so we can go back. So we know the capabilities, and right now we can compose a get observation request, for example. Get observation. This is a very simple get observation request here. So look at here. The first one's offering. So we know the offering name is Echo Node. So we put there, okay, I want the offering of Echo Node. And in this case, I want to observe property of soil moisture. Okay? And then the response format is as follows, text XML. And let me send to our server back home. And we should be able to get some data back. Okay, we got data when I was parsing it. Oops, sorry. Oops. Where am I? Okay, sorry. Let me send the request again. Okay. Okay, the data is back. Takes time to parse the XML. Actually, because this is a very simple query, it throws back a lot of data. Look at this. A lot of data. A lot. Okay, let's look at this OEM. So we know the bounded by is the bounding box for that observation. And we have the OEM member. Oh, so this is the observation. Okay? And the sampling time in this case is this. So begin to the end. And using this procedure and measuring this observed property, soil moisture here. And then the feature of interest is this guy. And it's a station. And then this is a station. The ID. Okay? And the location of that station. And finally, of the result. In this case, we use a suite data array. That's a way to encode the observation in a compact way. So it tells you how to interpret here the suite element type. It tells you how to decode these messages. Okay? So let's look at this. The first one tells you it's element count. How many elements are there? In this case, we got the 31,632 observation back. Okay, and then it tells you the element type. So step by step, you have different field. The first field here is the time. That tells you that actually this one, the first field, means time. And the second one is the water content. So that's this. Okay? So the first field is the time, the second field is the water content, so moisture. And then here tells you how to encode them or decode them. So the decimal separator is this. And then the token separator that separates the first field and second field is this. And then the block separator to add sign is here. Okay? So basically, you read the client need to read this in order to decode this. So this is one measurement, one observation. This is one observation, and so on and so forth. But some information they share some common information, and these are the common information they share. They use the same procedure, observe the same observed property, the same feature of interest. So this is basically an example of how you interact with a SOS. And of course, you can put some filters there. For example, I only want the data from April 10th to 11th, and then the bounding box, and then I can send the request, and this one should be much faster because data is just for a couple days, 1 day only. Okay? Okay. Any questions? So I encourage you to play. Use it and check it, and then you know what I'm talking about, right? And then actually the links are on the slides, and you can feel free to try. Yes.
One quick question: the limiters, are those the default values?
You can change.
What are the default?
I have to check the spec, but I know that can be changed. Yeah. Okay. So this layering diagram shows you if you want to implement your own SOS, how you implement, what are the components. Okay. So if you deploy the sensor in the field, basically you have a local sensor network. Okay, they can talk to each other using Zigbee or other network, other protocols, and eventually the data need to reach a gateway. So the gateway through a local transit network and hit the database. So, for example, in the field, this could be a Zigbee. And finally, you have a gateway. And the gateway can use a satellite phone. For example, it's very, very remote, like in Canada. And there's a satellite phone and insert the data into the database. And you can install SOS on top of your database and then reach to the web. So this is the typical layering diagram of how you implement a sensor services. So this is an SOS hands-on, so here's the link you can use. And then also there are other tools, very handy you can use, like I like to use the Chrome plugins. For example, in this case, you have the plugins here. You can just compose your own request. So this is more fun. Okay. For SOS, SaaS, we have the following implementations. There are more, actually there are 7 or 8, but these are the ones, basically they are working. The first one is Spatial North, and here's a link, and on the slides you can download it. So this is the most active one. And the second one is GeoSense. It's from us, my research group. And then, in our opinion, it's the easiest to use, very easy to install actually. It's a virtual machine, bang. Okay, and you have map server implementation and degree implementations. So these are the ones you can use if you are interested in deploying your own SOS. And actually, we also evaluate the existing SOS implementations. And I think for a healthy, sweet developer and user community, it's very important to evaluate ourselves regularly. I know WMS, like every year they have a WMS shootout. So basically they use the reference data set and compare the performance of different WMS. And they do it every year. So I think that's a great idea. And so this year, last term, I taught a course. So I asked a student to do a comparison of SOS. And in this case, he compared the 3 SOS here, Spatial North, Map Server, and Degree. And I'll show you the results we got. So basically, the testing data is we insert only a month of data because the writing is very, very slow. And then so we only a month of data. Sampling rate is 15 minutes or 5 minutes, basically. And observation, so we insert data. And so insert data for 101 sensor for a month. And then we use different request parameters to test the different implementations. And in the same testing environment. Basically, we use a virtual machine and the same settings on the same physical machine. So we know the performance is on the same platform. So in this case, it's the number of sensors and response time. So when you have more sensor, the response time, the lower the better. In this case, we found actually Degree SOS scale very well. And then Spatial North and Map Server, Spatial North second and Map Server third. So in this case is like this. So this is the number of sensors. And we also tried using bounding box so to test the spatial reference. So basically for bounding box, and also we test the bounding box size. So basically we have a bounding box size, and then we randomly put the bounding box. So and then average the result. Of course, still the lower the better. Again, we found when the bounding box size increase, the response time also increase. But actually, Degree is the slope is very good. It's very scaled very well. And again, Degree, Spatial North, and Map Server. And actually, Map Server, the response time grows pretty significantly. That's not a good sign. And in this case, we use the temporal again. We would choose the temporal, and then to try how they handle the temporal part. And then so 1 hour, 1 day, 1 week, and 1 month. And Degree performed very well. And then Spatial North and Map Server. And here we test. Basically, it's a combination of those tests. So basically, the darker the worse, basically. And Degree actually is doing very well. Okay, in terms of this is the response time, and this is too small. I can't even see. Okay, read the paper, please. It will be published, available on ACM Digital Library in November. Okay, and basically Degree is performed very well. So Okay, so these are our testing results in terms of performance. But however, it took our students a lot of time to figure out how to set up a degree SOS. And ask a lot of people, and the documentation is not very good, and it's very difficult to set up a degree. This are maybe because we are not good, but it's difficult to set up. And Field North is the most active community. You can find a lot of documentation, and it's not difficult to set up. Okay, and you can. And a good thing about Field North, if you're interested in SOS, Field North basically, you look at their implementation, it's like reading the spec. Yeah, it's one-to-one. I mean, yeah, if you read the code, you know the spec. So that's interesting. So it's a good reference system. And map server, same thing, difficult to set up, and because the documentation not enough. Okay, so just FYI, this is more practical issues. Any questions? Oh, promote our own server. Our server is very easy to set up. Yeah, but we didn't test our own server, well, for a reason. It's because we use document-based database, and it requires some configurations, and then that master student is not familiar with those configurations. Yes?
Does SWE include event specification language? How do you define event?
Event? Oh, yes, event, there's specification for EML, right? Event markup language. Yeah, so we do read that spec to do it.
They can be quite complex and can require a lot of...
Yes, complex events. Yeah. Event follow events. Yeah, so actually I'm not going to talk about events. It's a separate tutorial basically. Yeah. Okay, so we finished some parts, the information models, the interfaces, and then some evaluations. And right now I'll focus on application. Is that good? Applications. So 3 examples. So this is an example we did in 2005. We put some sensors on the ground. So that one is a radio, and this is for our data logger. And you can see a Hobo weather station, and then this is a solar panel, and we have this is a cell phone modem, and then this is our gateway, and the gateway basically wakes up every hour. And it's charged by the solar panel here. So as you can see, the gateway is hidden behind the solar panel, and that's a solar moisture probe. So what we did was we put 3, we call it smart sensors, in a very remote area, and do the continuous observations about the soil moisture. And then we also, the satellite get the satellite images. And the satellite, the temporal resolution is not good because the revisit time, right? But the good thing about in-situ sensor is it's always there. But the spatial resolution is not good. So by combining together, we should be able to get a better result. And the objective for this research is to predict the crop yielding. So basically how much crop I can get out of this land. And this is a very interesting research. So this is the architecture. So we have 4 sites, and then you use and this is the local transit network, and then you do the gateway, and to the this is local transit network, and the gateway goes through local transit network, insert into the database, and then publish in OGC services, and then we can access from outside, so make it interoperable. So this is the client we have. So basically, the goal was the farmer can go there and then look at the readings of the sensors. And this image, the image is the crop yielding prediction. So this is green means more yields, and this is the light green means less. And then so this the value of this, and actually this image is in WMS. So yeah, so it's both using both standards. The good thing about this is who are interested in this? The farmers, they are interested in the yields, and insurance company also very interested in the yields, because maybe when some disaster happen, right, they want to know how much loss, and then yeah, basically. And this is the example we did in 2005. Precision agriculture. This is a 3D client 3D SWE browser client. So it's using this is a Whirlwind, NASA Whirlwind open source. So we on top of Whirlwind, we put a SWE module there. And then we also have search engine. So basically this is a hit a SOS and get the weather data back. And then you can zoom in and then to get data. Because we get the data, each one is an observation, right? They have value, so therefore we can do some processing. In this case is Kriegen. We do the interpolation, Kriegen. And because they have time, so we can do this animation as well. We found it's very eye-catching in this case. So basically it's a surface and moves over time. Yep. And the data is from the SOS. And they are accessible. You can go to your Sense and to access it. Okay, because we use Whirlwind, so actually we can also access WMS. So we can put different servers, different data from different service SOS, and then data from WMS in a coherent environment. In this case, we access a buoy, SOS for buoys, and then the NOAA buoys, and then so you can see each dot is a sensor, and we also aggregate them. And so in this case, we access one WMS here, so you can get the water flow, and you can also get the buoy data. So this is pretty useful. So show you that in the same environment, you can access to different services and put different data sources together in the same environment. Okay, so this is one example, a 3D, for example, we have the Canada weather and the buoys in the same map window, and you can also zoom in to see that's the other WMS to show the radar images. Yeah. And actually we did some tricks how to load the data efficiently, so as you can see that the loading is pretty good. And I'll tell you how to do the loading later. Okay, this is one example. This is the second browser we have. This is a 2D browser on top of the big map. And again, the first step is the resource discovery. So we want to find where are the sensors. And then, so we load data, and then on the map, and you can search for the other sensor. In this case, water, you get the result back. And then can choose which SOS you would like to see, and add a layer, bam, and it goes there. So this is the other example about how we use Sensor Web Enablement. Basically, again, in the same environment, we are able to mix and match different sensors together. Okay? So here's the other example. What am I doing here? Yeah, just add more data, basically. In this case, it add one more layer. So you start to see 3 different layers together, different sensor layers or observation offerings. Okay, so the other example I will show you is, right now, it will be trendy to talk about, we have to talk about crowdsourcing. So in this case, it's a SWE, Sensor Web platform to do crowdsourcing. And it's called RockyView Whale Watch. And we work with about, the network, this application does long-term groundwater monitoring. And we work with more than 40 whale owners, so they own the whales. And they use this platform to upload their well readings. So in this case, the sensors are the farmers, well, and the tape measure. Okay, and why they are doing this? Because they want to know what's happening for their well. Okay, and then they want to know if they have water or not. Okay, and because also what's happening is it's possible their well, okay, they connect to the same aquifer. So the other farmer using the same well, or the oil company use the well, they want to know, if there's any illegal or they use too much water. For example, it's a concern. Okay, and we have data since 2008. And the good thing about this is a platform. So we have a coordinator do the QA/QC, quality control, and then I'll show you how to use this. So basically, this is we work with the domain scientists, but we found that to do crowdsourcing project is very important to work with domain scientists. They know the community, and they know what's going on, and we are just techies. So we have a scientist to do the QA/QC in this case. So she oversees all the wells. So each well is a feature of interest in this case. And then when a well owner, they can log in and look at their own well, and then they can add the reading. So basically this is the phenomenon time, and we ask them to do 3 observations, just in case that do 3 different readings, and then they can write down the notes. Okay, so metadata in this case, and then also they can see where is their well. But actually we don't display the real location for privacy issue, and then so on and so forth. So they can use this. And then they can also see the groundwater, the measurements, okay, about their well in this case. And of course, in this case, you only see this as a time graph, but behind the scene, it was the ONM XML document behind the scene. Differential privacy. The general public cannot see the actual location of the well. That's protect their privacy. And then the well information, in this case, we display like this, but the backend, that's a sensor ML. And then we also, actually, each one is a reading, actually. Each one is observation instance. So this is the phenomenon time. In this case, we do the average of the 3 readings. And then this is the metadata. So basically, these are the parameters they put there. Pump off 2 hours, they just put what they like, right? A dead bird in the well, something like that. And then when it's uploaded to the SOS, because only the scientists, they will do QA and QC, right? So if it's approved and to be uploaded to the SOS, so it shows it's complete, upload complete, approved is true, and you can also do some editing about those observations. Okay, and because this is a SOS behind the scene, okay, although it's a platform, it doesn't see SOS anywhere. But the same data set can be accessed through in a different environment. Let me show you, I guess. I can show you. For example, Rocky View. I can go here. So that's me. So I get to see, I'm a super user, so I can see everything. But I don't have a well. I can add a well, but anyways, I don't have a well. And so add well basically is to add a new sensor or in the offering. So I can go browse in this case. So basically the browse and they get observation request to the server, and you can get this and get it back. They can see the wells and you can get the data. So you send a get observation request again, and to fetch all the data in this case, and get data back and visualize in this environment. But what I want to show you is, because there's a SOS behind the scene, so actually I can access the same information in a different system. Yes. For example, I could go search. I search for groundwater. Ground should be fine. Okay, so I can get this groundwater, and then I can add a view in the map. So basically I want to show you is, although the 2 systems looks the same, but there are 2 different systems. So this demonstrates interoperability that in 2 different systems we can access the same information. So that's a value for suite basically. And you can also use any Future North client and to access the same information as well. Okay. But actually, in this case, we try to hide the standard behind the scene. So actually, the farmers, they don't know we are using OGC, yeah, for example. And I can show, because I'm a super user, I can hack into the others. So that's the scientist and the project coordinator, and she can see all the well information. And actually, in science, we found something very interesting already. So we found actually there are 2 wells. They are only 3 meters apart. But the one well, the observation recently goes up, the other goes down. And so that's make the scientists very excited because something's happening down there. And without this system, they couldn't observe that phenomenon. It also concerns the well owner as well. Okay. Other examples. SWE love Android. So there is an Android client for SWE as well. So you can see, in this case, you can choose the server, and then, or you can add your own server on your Android, and it shows you where are the sensors, okay? And you can zoom in and click, or I should say touch, and you can get the data like this on your Android phone. So, interested in more information, here's the publication. Or you can email him to get the implementation. So just show you that the phone can also access the SWE services. However, one of his result is one of the challenge is how to deal with a big amount of XML in the phone environment. And then, so actually this makes us think, okay, is SWE a good interface for mobile applications? Yes or no? We don't know. Let's move on. Okay, these are some examples. Any questions? No?
There are actually hundreds of more, too.
Yeah, there are hundreds more. Yes. This is very biased. I know what I know, right? So, SWE resources. Where to find systems, examples, developers, and friends. If you're interested in SWE, okay? And OGC technical committee meetings is where people show up and discuss. And then especially the SWE domain group. And so the coming week we have a SWE domain group meeting, so you can see what's going on. And then also the IEs, they have a lot of, basically they apply SWE in a domain. For example, the groundwater interoperability experiment. They use SWE as the framework they are using for serve their data, and the service IE as well. So these are the ones you can find, and where to find all the email lists you want to read. Hydro domain working group as well, but that's they cover both groundwater and surface water. And also on the research side, we have a workshop on Sensor Web Enablement. So we have been this year is the 4th year, and then this year is we joined the ACM 6 Spatial GIS conference. So if you are a researcher, that's where you can meet other people, develop a SWE and doing SWE research. And also a good place to start is the OGC network. If you go to the OGC network, you can find a lot of resources there, and then where to find a spec, what are the implementations. Like Carl said, 100 more over there, and then you can look at it. Okay. And Filter North is the most active open source SWE project. So actually you have a lot of things going on there. And the good thing about this implementation is in my opinion, it's like a reference model. It's read the code is like read the spec. So it's very easy to understand and help you to understand the spec, which is a good thing. And our SOS is very easy to install. So if you want to set up a SOS very quickly, and you can download the virtual machine. So basically download a virtual machine and you have a SOS running, okay? And then how to feed the data into SOS, we use Excel. So it's basically CSV, and you can upload CSV to our implementation. So it's easy to upload. You don't even need to know any database configuration. Okay. So those are resources you can access. So they are on the slides to help you after this tutorial where you can start. And then I want to talk about research. Some of the interesting research direction I think for me is interesting. Okay. So why it's interesting? So I'm thinking, okay. So WWW is one of the most active research area in computer science. Yeah. WWW conference is very difficult to get in. Rejection rate is very high, 90%. But it also brings huge impact to our daily lives. And a good example is PageRank. PageRank was a research paper. And then in the paper of PageRank, they said they have an implementation called Google. And it became Google. Okay, so it's interesting. So how about GeoWeb and Sensor Web? So there are also many exciting research questions for us to tackle, I believe. And very interesting. And so these are interesting topics. I think interesting. Very biased again. The first one is how to find sensor observations, and I think that's very important. And it's also very important for OWS, basically so for web mapping services. So how to find what are the maps online, the WMS online. Okay, and you say you can have registries, so on and so forth, but I think that's an interesting research topic, or the work we should do. And the second one is how to browse sensor observations. And then especially in the future, we might have 10 to 20 billion of them. Oh, typo. Billion of them. And then, so, yeah, how to do this is very interesting to me. And third, how to detect events and receive notifications. And that's a scalability problem, how to process them. So first one, search and catalog. And so before we talk about search and catalog, we'll think, okay, how to evaluate the search engine? So how do we know we can do a good job? And then these are the four. I learned that from BIM, actually this is what they share in the conference. So first one is relevance. So for you to search on the web, which you want the result to be relevant to you. So same thing, when we search a sensor web, we want the return, the result should be relevant to me. So these are the sensors I want. And this is very difficult. Second one is completeness. So how do I know the result is complete? So cover all the sensors in the world. The third one is freshness. How do I know, okay, or you want to guarantee the user the result is very fresh. There is a new sensor online and then we are able to capture it, okay? And the fourth one is performance. We are not patient. So be like this, okay? So you only have time to access, no time to query. And then, so these four is when we develop something for search, like sensors, and we need to meet the following requirement. And so I found this an interesting research area. And then we did some initial efforts for this. So if you want to know, or you want to search for OWS resources, you can go here. So actually, I can show you here. And if you want to search for, oh, no, this one. You want to search for what's out there, OWS resources out there, you can go here and search. For example, you can get the keywords, for example, ice, and you search. And then it returns what are ice, the SOS about ice. You get to preview as well. And then, but we also cover maps. For example, is there any ice, WMS about ice? So maybe one not complete, right? And water, for example, how about WMS about water? So we find these WMS about water, for example, in this case. And then you can view it in the map as well. So this is a preview, so this is hidden WMS. Okay, so this is the example we have. And here's the architecture. This is very preliminary because the student left. She didn't finish her PhD. We have the crawler, on top of the crawler, and then we try to get the, we assume if somebody published a web WMS or SOS, the organization should have leave some trace on the web. So we try to Google, Yahoo, and Bing those keywords, or the keywords, the combination of keywords, and get the result back, and we try to find what are the valid ones. And we need to parse after we find the links, the endpoints, and then we send the get capabilities document to them, and we parse the content to make sure they're alive and the content, and then after clean them, filter them, we put the OWS capabilities database. And the research part interesting is the analyzer. So how can we analyze? By analyzing the capabilities and these other information, we can make sure the search result is relevant to the users. So this is interesting to us. And then, so this is the architecture. And the other thing is, and the result is we found about almost 90,000 WMS layers and almost 60 SOS out there, about 6,000 SOS offerings. And when we can also analyze, with the information, we can analyze, find some interesting results. For example, we can find, in our observation, we found more than half of the OGC web service sites are in Europe, and then some in Asia, and some in, almost the other half is from North America, for example. and also the top 10 countries about the OGC services. And however, we use English, so actually it is possible that we miss a lot of services in other languages, but should be fine. I don't know. Yeah, and then also can find the vendor share. The interesting is we don't know. Most of the services we don't know who developed the WMS. We cannot find the queue over there, or we don't know how to find the queue. And then, but we found S3 and web server is very popular. Geo server 2%, so on and so forth. And this is about big data, right? To get the data for unintended use. Okay. So next one. We think browse is very interesting as well. So, for example, we have a lot of portals, right? But we want to browse information. So we define to browse is to casually look through something in order to find items of interest. So it means casually. When you browse the web, do you always know what you want to find? No, you browse, right? You casually and you find what you can find. And then, so we think that's very important. You are able to browse. And I show you this already. This is one browser example. So basically you can see what's available out there and you can add into your browser. Okay. And then, but an interesting thing is this. When we use Google Map or WMS tiles, and we load tile by tile, right? So as a result, the performance is very good, like tiles just coming in. But how about sensors? Can we manage them in like tiles? However, sensor observations are space and time, right? So basically they are cubes. Okay, so how to efficiently load those cubes is interesting. So as a result, we developed some framework to do that, and then we will go over detail. So basically is we manage those loadings, and then actually for this, for example, when we look at this, when we load the observations, we load cube by cube. So gradually, and then put them together. So actually the performance is pretty good in this case. But the other challenge is a lot of the thing when we load, and they are empty response. Okay, because there are no observation over there. There are no observation in this time and space. So actually, how to reduce the empty, the unnecessary request, which is an interesting problem to tackle. Okay, this one is interesting. I want to show you. Here, I have a video. Well, my student make this for a student video competition, but we didn't win anything. Yeah. More other better videos out there. So basically, this is the multi-facet-based browser. So allow you to filter according to different criteria. You are able to quickly filter out the layers you don't want and to find the layer you want. Right? You can filter using like the realms, or it's a water, or keywords, or the country, for example. And you can even have the histogram, for example, and group them together. And then when you zoom in, you can even see the preview of that data, and then one click gets you on top of it. So this is one example we show that this kind of system might be very useful for scientists. And this is just the first try because this is just a very simple filtering. But how to automatically generate these tiles and then extract keywords from the metadata, right? And then the bottom-up approach to extract metadata, that's interesting. But in this case, we use humans. Basically, a student manually generate all these. But this can be a useful tool for scientists as well. And the other way is we also believe that we mentioned about suite, we tackle the semantics as well, right? So we believe actually, in many cases, when you search for data, do you care about sensors? Do you care SOS? In a way, I don't care. I want the system enable me to show me the soil moisture data in the world, right? Rather than show me the soil moisture data from this server or that server. I want everything. So as a result, we did something to allow you to browse phenomenon rather than sensors. And I can show you a demo. And then, so this is from the semantic point of view. And then, for example, in this case, so you can even choose a taxonomy, different taxonomy, for example, different taxonomy. So how to organize the phenomenon, okay, different ontology. For example, I'm interested in soil temperature. So there must be something wrong because there's no soil moisture in the ocean. But you get the idea, right? So you click a phenomenon, it gets you the result from different SOSs. So you integrate different SOSs together in the same one, in the same environment, allow you to browse with the taxonomy, ontology, rather than you hit SOS one by one. So this is one thing interesting for us, and I think this is interesting research as well. How to automatically and find the relationship between these layers, phenomena. That's interesting. And also, how to integrate social network with sensor web is also interesting because we believe that if you can find in many cases, you don't even know what sensor you are interested in, right? I'm interested in this study area, and then it's very possible that I don't even know what sensors are available, or I might be interested in that area. But if I can find a person who is an expert for that area, he uses a lot of sensors, I might be able to find information. So that's a social network part we can use. So for example, how to recommend sensor to people, right? Like you recommend books in this case. And then, yeah, I don't think we'll go detail today. Yep. But basically it's how to recommend. And finally, I want to talk about IoT. I think it's very exciting. And we did something to put the SOS into a device like a matchbox size, or a little bit bigger than matchbox. This big. Okay. And then this one, combination of them is less than $100 US dollars, and the price will go down significantly in the future. And then we put the SOS into this small thing. Okay, it has a wireless module, and in this case Bluetooth. And as you can see, it has Ethernet cable as well. So you plug into Ethernet, it's a server, and then itself is a SOS. So basically, we try to test if we can put push boundary and put SOS into a small embedded computing system. And yes, we did, but with a lot of challenges. Finally, we found this interesting. There will be sensors surrounding us very, very soon. These are the ones I found you can purchase online right now today. Actually, both Nest and Wemo, you can buy it in Apple Store. And I have a Nest. Actually, it controls my house, the temperature of my house. And for example, actually, right now I can try to wake up my wife by make the house very, very hot. And it's creepy. And Nest has a lot of sensor in it. It has an infrared sound, so basically it can detect you are home or not. Very scary. Okay, so for example, yesterday I went back home and I found the Nest detect I'm back and then turn on the heating system. It's scary. And also with the Wemo is from a company called Belkin. Actually, I heard a couple days ago, Belkin acquired this technology from a professor in UW with $100 million. Wow. And then, so allow you, basically it's something you can plug onto the plug, so you can control that plug through using your iPhone. And why I think it's a scale and connect to the clouds, allow you to monitor and upload your weight data automatically. And Kobachi is a soil moisture sensor and allow your plant to talk. So I didn't buy a Kobachi, but I tried the program. Basically is, you can name your plant, okay, Harry, for example, and then you put the Kobachi there, and then Harry will tell you, I need more light, I need water, I need fertilizer, or I'm dying. So these sensors are just, try to embed themselves into our lives very, very quickly. And then, problem. Wemo has their own system. Nest has their own system. Ything has their own system. Kobachi has their own system. We'll see this getting worse and worse. Each sensor has their own system. But actually, I can see a reason to combine the data from Nest and with the data from Kobachi. Okay? Or, I'm not sure about Ything or Wemo. And then, however, there's no way they can interconnect or share the data. And each company, actually, they really want to use the data for their business model, right? And then the other thing is, think about today, when I buy a computer bag, okay? So, may I use my computer to connect to internet, to different service provider? Yes. But in this case, when you buy a Wemo, you have to use their services. So actually we envision one day, so if it's possible, when we have a standard, so when I buy a Wemo bag, I can choose which service provider I want to choose. Because they might provide a better service. They might provide a better data analytics model to mine my data, right? Or I want to just share data from all my sensors at home, right? Although I purchased them from different companies. But right now, you have to just stay within their system. So I think this really make a good case about a standard to enable an IoT interoperability. And I think we have a good chance there. And I think that's it. That's today's presentation.